Welcome, Calc class. Good to talk to you. I'm going to let you watch my hands do some math for a while. I'm going to pick up in the book where we left off and talk about implicit differentiation. There you go. See, there's the title. Using my tablet to record, and then I'm going to throw it into Google Classroom. Real fun. So implicit differentiation is an application of the chain rule, and it allows us to take derivatives of functions that are written implicitly. An implicit versus explicit function. An implicit function, the x and y's are, no better way to say, I guess there's a better way, but are mixed together. Whereas explicit functions, y is a function of x. From up to this point, we've been taking derivatives where y is some function of x. So if you have a standard form of a line, 2x plus y equals 5, that's an implicit form of the line. Solve that for y, subtract 2x from both sides, and you get the explicit form. Equation of a circle, solve for y, subtract x squared from both sides, take plus or minus the square root, and you get two separate explicit functions, the top half of the circle and the bottom half of the circle. Right. Problem with explicit functions is sometimes they're really, really hard to find. Right. So here's an implicit function. This is actually the graph of or the function whose graph is a hyperbola, and because of that minus sign, and these two is product of x and y. Okay. Now, if you try to solve this for y, you could do it. You got to really do some funky algebra. But I'm not going to do that because we don't need it. All right, so here's the implicit form. The explicit form does exist. Sometimes we can find it algebraically, sometimes we can't. But we're always going to assume that we can find it. Right? And then we're just going to use this with our derivatives. Right, so that's the first step for taking the derivative of an implicit function. You assume y could be written as a function of x, but you say, well, I don't really need to find it because I can use the chain rule whenever I come across an expression for y. Now, so if you had something like this, y equals 5. Okay? That happens to be an explicit form, but you still could say, all right, y must be some function of x out there. So if I want to take the derivative of this, say, okay, if two sides of the equation are equal, then if I take the derivative with respect to x of both sides of the equation, okay, I'll get a new equation that shows the relationship between their derivatives. So say, okay, what is the derivative of y with respect to x? Well, I don't really know what the function y is, but I can just call its derivative dy dx, or I can just call it y prime. The derivative of y is the derivative of y, whatever it is, okay, equals, and then the derivative of 5 with respect to x, the derivative constant is always 0. Okay? So nothing new. If y equals 5, y prime equals 0. Take y squared equals 5. So, okay, well, that's not a function with x's in it, but let's assume that y is some function of x. I just don't know what it is. So if I knew what it was, it would be inside, think about it, inside a set of parentheses, raised to the second power. Now I want to take the derivative of this. I don't have a lot of space here, so I'm just going to put it on the other side. Doesn't matter. Okay. This just says take the derivative of all the terms in this equation. Well, the right side is easy. The derivative of 5 is 0. Now you take the derivative of something squared. And this is where the chain rule comes in. you're assuming y is a function of x, an expression with x's in it. So if I had something squared, the general power rule says bring down the exponent, leave the base alone, reduce the power by 1, but then to deal with the rate that's inside this base function, I have to use the chain rule and chain onto that the derivative of the inside function. But the derivative of y is just the derivative of y. It's y prime. So whenever you take the derivative of the variable y, you just call it the derivative of y prime. All right, so now 2y times y prime equals 0. Okay. So all this parentheses stuff, after a while you don't really need to write it, but just it's just a good way to look at it, to think about. All right, so now I can take this expression and get y prime by itself. So I'll divide both sides by 2y, and I get 0 over 2y, which in this case, y prime again just equals 0. But that I was just showing you the process for this. So powers of y, the chain rule always comes into place. So if you just had, you had an expression in somewhere, you had y cubed. You could think about that as being something cubed, so its derivative would be 3 times what's inside parentheses, reduce the power by 1, and then chain onto that the derivative of the inside function, which is just y prime. Okay. So any power of y works that way. Y to the 11th. Y to the 11th looks like y double prime. Let's do y to the 71st. And so if I'm taking the derivative of that, it would be 71 y to the 70th times y prime. That's it.